So let's move on with our discussion on gate sizing, right? So what was the summary of gate sizing? If you have some arbitrary circuit, okay, with a path logical effort of G, which is equal to product of the individual logical efforts, right? And if the load capacitance is some value CL, right, and if this input gate presented a capacitance of C in, then the path electrical effort was CL by C in, and this again, by the way, is just the product of the stage electrical efforts. So the path effort F is just G into H, right? And we said that in order for the delay to be minimum, each gate had to do equal effort, right? Of course, the equal effort is not in terms of arithmetic mean, it's in terms of the geometric mean, right? F power 1 by n kind of thing. So the stage effort, optimal stage effort, optimal Fk is F power 1 by n. So that the job of charging the load capacitance is sort of evenly distributed amongst all the gates in that circuit. Okay, this circuit could contain any number of, it contains n gates. That's what this n is. So it has n logic gates. Okay, and therefore the minimum delay was n into F power 1 by n plus P. And what is P? This is nothing but summation Pi, parasitic. Unlike the path logical effort and path electrical effort, the path parasitic effort is just the sum of the delays. It's not the product of the delays. Okay, just keep that in mind. So we did some examples, and in one particular example, we basically took an inverter, a NOR, and then another NAND, both 2 input, final inverter, and then we made it drive a very large load capacitance, assuming that this is a 1x capacitance. It turned out that for this particular circuit, the optimal stage effort, I'll just say F opt, was 10,000 power 1 by 4, because there are 4 gates, and therefore this was 10, and the minimum delay was what? 46. Normalized minimum delay was 46. The thing is that from this formula, it is evident that if n happened to be a very small number, then this F power 1 by n can come down only by that much, because you have only a square root or a cube root or a fourth power to, fourth root to take. And with that, you cannot reduce this delay too much, right? Remember that though delay is scaling with n, that means if I increase the number of gates, the delay will go up, because there is a multiplication by n. The power of F power 1 by n is much higher. It is bringing the delay down significantly, right? And therefore we said that if you have a path with very few gates driving a very large load capacitance, even this delay is technically not the most optimal. It is optimal given that you have only those many number of gates, n gates. That is true. But if I am allowed to increase the number of gates, then there is a chance that you can reduce the delay, right? And we discussed yesterday that in order to add any gate on the path, the best gate that you can add is the inverter, because the logical effort is 1. Okay, so we are going to now look at the problem of buffer insertion. So I'm going to take my old circuit which I had a path logical effort of G, path parasitic effort of P. Okay, and this was my C in cap, and I had a load cap here, CL. Okay, so the path logical effort is G, and there is a H, and there is a P. Now I am going to alter the circuit as follows. Same C in, because that doesn't change. Then I start inserting inverters in the path. Some number of inverters I'm going to put. Okay, I'm not going to worry about the logical inversion at this point. See, okay. So this is G comma P. That doesn't change. So what is the new path logical effort? Is, yeah, it is just G into the product of the logical effort of all my inverters. Correct? How many inverters am I adding? I'm going to add, let us assume that there are N1 gates. I'm going to add N minus N1 inverters, so that the total number of gates in my new path will be capital N. Okay, so this is still G. Now what's my new path electrical effort? Same thing, it's output load capacitance by input load capacitance. That is not changing. So that is also equal to H. Correct? What is my new parasitic delay? P hat. Right? New parasitic effort is what? The old parasitic delay plus the delay of N minus N1 inverters. So that is something that is quite obvious. If I add inverters, I am adding a delay penalty of those inverters, right? The only advantage is that delay goes linearly, the other thing comes down exponentially, and therefore I will still gain. That's the intuition. So this is P plus N minus N1 into, I'm going to call the parasitic effort of the inverter as P in. Okay, it's actually 1, but I'm just giving it another variable because there are other inverters that I can construct which have parasitic effort less than 1. Okay, so we'll do that later. P in is parasitic effort of inverter, which is equal to 1. So if I now have total number of N gates, what's the minimum delay that is achievable in this circuit? The D min right, is simply going to be n into g hat into h hat power 1 by n, right, plus the parasitic effort of the entire circuit. What is that? That is P plus n minus n, n1 into P n. Of course, we know that this is nothing but n into f power 1 by n. Okay, so if f is equal to g into h for the old circuit, then f hat is equal to g hat into h hat is also equal to gh is equal to f. That doesn't change. Okay, n into f power 1 by n plus p plus n minus n1 into. Now, what was the delay of this earlier circuit here? Right, I will say d min hat because that's my new circuit. The d min here was n1 f power 1 by n1 plus p. So it's important to note that these two values are the same in both equations. I have only increased this n1 to capital N, a larger number, and of course thereby I have incurred a linear increase in delay of the parasitic term, correct? So now I want to find the optimal number of inverters that I can add in the path which will make my delay an absolute minimum, right? So what do I do? Dou d min hat by dou n equal to 0. Correct? So can you please differentiate this and set it to 0 and tell me what you get? Do you get this? You can write this as f power 1 by n into 1 minus ln of f power 1 by n plus equal to 0. All of you get this? Okay. So now let the optimal stage effort equal to, I am going to call it as rho as f power 1 by n. Okay. implies I have the equation that I want to solve is rho into 1 minus ln of rho plus equal to 0. Okay. Now, if P in is 1, we are talking about a standard reference static CMOS inverter, right? Not reference, static CMOS inverter, then this will simply become rho into 1 minus ln of rho plus 1 equal to 0. Of course, the problem is you cannot solve this analytically. So, you have to find the solution numerically, and it turns out that when rho equal to about 3.59, you can evaluate this and check for yourself. This quantity on the left hand side will be very close to 0. Okay. So, therefore, it turns out that the optimal stage effort is about 3.59. Okay. Now, 3.59 unfortunately is not very good when I want to do gate sizing, because even yesterday I didn't talk about it. We got some answers for the gate sizing. We got fractions. All these fractions are actually not available to you, right? Because I have gates which are of fixed sizes, 1x, 2x, 4x, and you know, sometimes if you want some very special gate, you can make an arbitrary width as well. But mostly from the standard cell library, you will get only fixed gates. So, you have to, after you get this continuous solution, you have to discretize it. Okay. It turns out that discretizing this optimal stage effort to 4 is not a very bad approximation. It turns out that the delay goes up only by about 2%. Okay. So, my rho opt, which was 3.59, can be approximately made 4, and the D min will go up very slightly. Okay, it's not too much of a problem there. So, therefore, it's an accepted approximation to make, and that is why you will find this fan out of 4 to be such a magic number in digital design, because that is the fan out, or that is the optimal stage effort that is going to give you the minimum delay. So, if I want to send one signal from here to there and I want to buffer it, then what would I do? I would simply go in sizes of 4x, 1x, 4x, 16x and so on. You get the reason is the theory that you do here. Inserting buffers and getting an optimal stage effort of approximately 4 is the best that you can get. You can't get better than that. Clear? So, of course, now we need to translate this into how many buffers we wanted to add or how many inverters we wanted to add. So, of course, this rho opt, we defined it as f power 1 by n, right? Therefore, if I just take a ln on both sides of with base rho opt, I would get 1 equal to 1 by n log to base rho opt of f. Implies that the optimal number of stages is log to base 4 of f. Yeah. Yeah. Correct. No, so that's what I'm saying. If the circuit changes, then the number of inverters that I have to add will change. See, this depends on f. It turns out that irrespective of the circuit, the optimal stage effort is still 4. It doesn't matter what the circuit is. That's a very good point. It's only the number of inverters that I add will change depending on the circuit that I am trying to optimize. Okay? So why don't we go ahead and apply this to the previous problem that we solved yesterday. You know, we did this problem, right, where we got this. Can you now tell me how many buffers I need to add, or how many inverters I need to add to the path, right? And what is the minimum delay? Remember that the minimum delay that you get after inserting buffers should be less than this. Otherwise, it's a useless exercise. Without buffering, we got a delay of 46. Now you tell me how many buffers you have to add and what the minimum delay is because of buffering. That has to be less than 46. Clear? So can you solve that? So what did we have in that circuit? An inverter, a NOR, NAND, another inverter, right? These are my N1 gates. I am now going to add some number of buffers and put this load capacitance here, 4500X. This is 1X. So what is the optimal? So what did we get as F? 10 power 4. And how did we get that? We got it as 20 by 9 into 4500, which is basically 10 power 4, right? So therefore the optimal number of gates should be log to base 4 of 10 power 4. What's that number? About 6 point, yeah, you get 6.64, right? So now what do you do? If you are okay with logical inversion, you could even accept 7, because of course there are how many? 4 gates here, so I have to add 3 more inverters, right? Or if it's not okay, then I can add only 6 of them. Either way, you will get a delay which is lesser than that 46 that we got earlier. So tell me, what is the minimum delay we get because of this post buffering? N opt equal to 6 or 7. Okay, let's take 6 so that we don't want any inversion. We don't want logical inversion. So let us take 6. I want to make this 6. Therefore, D min is 6 into 10 power 4 power 1 by 6 plus the parasitic effort of the circuit, original circuit. How much was that? 6 plus how many? No, 2, because I added 6 gates totally, right? So 2 into 1. What's the number you get? Yeah, 35.8 as opposed to 46. So who was the guy who gave you maximum benefit? It is that f power 1 by n. I allowed that f power 1 by n to go to the 6th root, and that killed the delay significantly. So even though I am adding inverters and actually incurring a delay penalty, I am still reducing the delay of the circuit eventually. Okay, so let me just quickly summarize gate sizing problem that we looked at. So gate sizing, if n is fixed, that is the number of gates in the path are fixed, then the stage delay should be made, or the stage effort should be made equal for all the gates. That is, the optimal delay is n f power 1 by n plus capital P, not small p here. If n is variable, I can do something about n, then I reduce n into f power 1 by n by increasing n. Right? This is the counterintuitive part. Optimal stage delay or stage effort should be approximately 4. Okay? And therefore, the optimal number of gates in the path should be log to base 4 of f. Right? Then the optimal effort again is this particular number. It's not just, actually tau op should be n hat f power 1 by n hat plus p plus the inverter delays. Right? So these are two methods in which we have reduced the delay of the circuit or optimize the delay of a path, not a circuit. Yet. I'll tell you how to do it for a circuit later, though it's not part of the syllabus. Question now is, we have optimized n. We have done all that we could with n. The only thing left for us to tweak is to tweak f if I want to reduce the delay of the path any further. Now, if I want to reduce the delay of f is G into H. What is H? H is output load capacitance by input capacitance. That is fixed because I have to drive a fixed capacitance. It's coming, that's a specification coming from outside. I cannot tweak that. So the only thing left for us to tweak is the path logical effort G, which will simply translate to the gate logical effort Gk. In order to reduce the delay of a path any further, I need to reduce the logical effort of the gate. Remaining part of this module will be discussion of various styles of CMOS gates where I simply reduce the logical effort significantly step by step.